Okay, so let's begin. Let's continue our discussion about the Fourier series. As you may remember, we have been seeing some Fourier series properties. These properties we have listed are critical for solving questions. Today I will write down one further property, which is also important in solving many questions. And starting with that, with the knowledge of that final property, anything you want to ask? I just heard something, or maybe it was a mistake. The property that we are going to see now is the eighth property, and that is the differentiation in time. So we are going to take the derivative of our input signal and what's going to happen to the Fourier series coefficient of that. That property is, again, not very complicated. It's quite easy to prove, to make a proof. We know that x of t is summation of, let's say, ak e to the j k omega 0 t, right? With a fundamental frequency of omega 0. So integer multiples of that fundamental frequency will make the harmonics, and those harmonics will be scaled by the Fourier series coefficients, and we are just combining them. This is x of t. Now, suppose that you have a y of t signal, which is x prime of t, or d by dt x of t, the time derivative. The first thing that you must immediately understand is the fact that the time derivative of a periodic signal is also periodic with the same period. For instance, if you have a cosine, we know that its derivative is sine. And if you have a sine, its derivative is cosine. And they have the same period. But of course, the scales may also change depending on the frequency. We know how to take the derivatives. So what happens when we take the derivative? With this kind of a representation. Let's do it. Let's say that y of t is equal to d by dt x of t is equal to this infinite summations time derivative, and that is ak times j k omega 0 times e to the j k omega 0 t, right? Simple. From there, we can deduce that these are the Fourier series coefficients of y of t, because they are the ones that scale the harmonics. So we can call it bk. So the property tells me that bk, which are the Fourier series coefficients of ak's, of y of t, are equal to ak times j times k times omega 0 for all k. This is the differentiation property that we want to see. Now, we can use these properties in solving a lot of questions. In many of the cases, we don't really find the Fourier series coefficients of signals by the integration, by the formula. We don't want those formulas anymore. So I'm going to open a new page, and I'm going to start solving a few questions about applications of these things, of these properties. And they are actually related to what we have seen as the properties. By the way, before starting the example, since the second example or the third example, we require that, I have to indicate one important issue regarding this last property of differentiation in time, and that is, except for k is equal to 0, because when k is equal to 0, it actually corresponds to the DC coefficient, B0 or A0 or whatever. So you should better take care of those, the DC coefficient, A0 or B0 or C0, whatever, separately, okay? So this property, the differentiation in time property, is valid for the coefficients with an index k different than 0. It can be for -1, +1, +2, -5, etc., but not k is equal to 0. And there's also a dual equation for that. If you integrate a signal in time, then you are going to get something like this. It may be, for instance, you can say z of t is equal to integral from minus, it's not really minus, it's within one period, but I have to be careful about how to put it. It's from a point A to a point A plus t or something like that, x of tau e to the, no, there's no e to the, x of tau d tau. So it's the inverse operation of what we have been doing in time derivative. It's the integral. And over there, you will come up with ck, which are just the reciprocal versions of this ak times j times k times omega 0. So we are, while taking the derivative, we are multiplying with jk omega 0. And if you're integrating, you are dividing by jk omega 0. It's actually quite simple. 1 over jk omega 0 times ak. Okay, it goes on like this. In the derivative, you're multiplying with jk omega 0. In the integral, you're dividing by the jk omega 0. But again, for k different than 0, not for the dc. You have to handle the dc coefficient separately all the time. It's a necessity. Okay, now we can continue or start some examples, seeing some examples. Let's think of this signal, which is a half duty cycle signal from 0 to 2, it is 1 over 2, and from 2 to 4, it is negative 1 over 2. And then it goes on as a periodic signal like this. So it is a periodic signal that I am considering. Let's call this signal g of t. And the question starts by asking, what are the Fourier series coefficients of this g of t? This g of t will be a fundamental signal to which I will relate a derivative and an integral. Okay, when you integrate this starting from 0, it will give you a different signal shape. So we will evaluate the Fourier series coefficients of that. And when you take the derivative of this one, you may be a little bit concerned about the sense that it is discontinued at 0 and at 2. But if the discontinuity jump amount is equal to 1, then its derivative is defined as delta of t, a unit impulse. If the discontinuity jump amount is 2, then, for example, it will correspond to 2 times delta t. Okay, so there is actually a defined derivative of a discontinuity, a jump, in this format. Because we know that the derivative of u of t is delta of t, and the integral of delta of t is u of t. Using that analogy, we can handle these, the derivative of this one as well. We can do that. But now, this is our signal. This is g of t, which can be constructed from a signal that we already know, which we can call x of t. and that x of t is essentially from -1 to 1, it is 1, and the period is 2, and therefore starting from 3, 4, 5, etc., it is also periodic, like this. This x of t is, or was, an example that we have solved. We know the Fourier series coefficients corresponding to this x of t. It was the first example that we saw, actually. How did we find the Fourier series coefficient for this one? The Fourier series coefficients were obtained by the integral formula, and it was not very easy. Now that we know the Fourier series coefficients of x of t, we don't need to find the Fourier series coefficients of g of t anymore, because we can write g of t in terms of x of t as, let's say, x of t minus 1, which corresponds to a delay to the right-hand side, and then I can subtract 1 over 2, for example. So I shift it to the right, and I subtract a 1 over 2, making the offset or the bias of minus 1 over 2. Now, we can use all the properties to reflect the Fourier series coefficients of x of t to the Fourier series coefficients of g of t using the time delay formulas and all those things. Remember the properties in the previous page that we have seen. We are going to use them, except, of course, the DC coefficient, the zeroth Fourier series coefficient. This will have the Fourier series coefficients, let's say, BKs, and from here, I can say that the Fourier series coefficients of x of t minus 1 with respect to the Fourier series coefficients of x of t, assuming that x of t Fourier series coefficients are AKs, then x of t minus 1 will have a Fourier series coefficient corresponding to AK times e to the j times k times 1 times omega 0. Or it's going to be like this, e to the minus j k times minus 1, because the shift is t minus 1, as you see, times omega 0, okay? But what is omega 0? Omega 0 is 2 pi over capital T, and capital T here is 4. The fundamental period is 4. Therefore, it is 2 pi over 4, and that is pi over 2. So in this example, omega 0 is pi over 2. So I can write this thing as AK times e to the jk pi over 2. It can be reduced to this format. Now, how about this new term, this additional term, minus 1 over 2? Now, as you see, it's a constant term. Therefore, it doesn't really affect the Fourier series coefficients for k different than 0. It only affects the DC coefficient. And we are going to evaluate the DC coefficient of our new signal, g of t, separately. So that minus 1 over 2 actually does not disturb or change any Fourier series coefficient. It doesn't affect anything. Previously, the Fourier series coefficient, the DC Fourier series coefficient was 1 over 2 for x of t. So I can see it. A0 was 1 over 2. But now I can see that B0 is 0 because it's positive and negative completely symmetric. So with this thing in mind, I can say that BK, of course, for k different than 0, is equal to I'm not sure if this is a plus or a minus. You will have to check it from the book, because the example may exist in the book. Is there a minus sign here eventually or not? Can we just check the previous page and see what is the time shifting property. Yes, the time shifting property states that if y of t is equal to x of t minus t0, as we see here, then bk is ak times e to the minus jk omega 0 t0. So I have to go to the new page and put a minus sign, because if it is already x of t minus t0, there is a e to the minus j, etc. t0. So we have made a mistake at this point. It's actually this with a plus, and therefore this makes a minus sign here. So, but you will have these properties anyway in your hands, available in solving questions, so you shouldn't worry about these technical details. So this is the correct, now we understand. bk is equal to ak times e to the minus jk pi over 2. Do we remember what AK is? Well, you can check out the answer from the first question. It is sine times pi k over 2 over pi k. So I have to multiply this by e to the minus j k pi over 2, of course, for k different than 0, and b0 is equal to 0. So you can put it in a box and say that I found it. This is it. You don't have to simplify this. I don't think this needs any further simplification or anything. This is just, these are the Fourier series coefficients that we are looking for. I'm pretty much sure that if you try to take the integral of this rectangular box periodic signal and take the integral formula, and from there, if you want to just combine everything and try to simplify it as much as possible, it will still be very difficult for you to come up with this bk expression, sine pi k over 2 over pi k times e to the minus j k pi over 2. It looks difficult. So that's why you need to apply the properties. That is a critical tool for us. You may consult to the integral equation or integral formula for the expression of the Fourier series coefficients only if you are desperate. If no property comes to your mind, if you cannot think of anything else, your last desperate attempt could be taking the integral for the formula. But I don't think you will have sufficient time for solving those questions during the examinations. So please exercise with the questions in the book, at least, and try to understand when a property needs to be applied. Now, a different question that is somewhat related to the previous question, this one, is the integral of g of t. Or you can think of it like this: it is a new signal in such a way that when you take the derivative of that new signal, you get this signal. Okay, you can think of it like that. And that signal is this. A triangular train. Let's give a name of h of t, although it's not a system, but I'm using, you know, g, f, etc., h for some signals. And this h of t here is 2, this is 1, and the peak of the triangular waveforms is at 1. So do you see that from 0 to 2, the slope is 1 over 2, so the derivative is 1 over 2. And from 2 to 4, the derivative is -1/2. Similarly, from -2 to 0, the derivative is also -1/2. So as you see, if you take the derivative of h of t, that's going to give you g of t. Okay, this is what you are going to get. So what are the Fourier series coefficients of this h of t? We are going to use a simple property saying that h of t will have Fourier series coefficients, let's say ck, which is the integral of g of t. I'm putting it like this. I'm not going to use tau, d tau, or anything. It's just the integral of that. Or you can also say it more properly using this. And this is equal to, do you remember the derivative formula? It was jk omega 0, a multiplication by jk omega 0. So I'm going to divide by jk omega 0, 1 over jk omega 0. I'm going to put, I will replace omega 0 later on because now it's in the formula like this, times bk, where bk is this one. Okay, like this, these bk's. Of course, 4k different than 0. Still, I have to evaluate the DC coefficient, that is C0, separately. But for the others, this is the formula. And this formula reads as 2 over jk pi, because pi over 2 is omega 0. 1 over omega 0 is 2 over pi. So it's there. And then I will put sine pi k over 2 divided by pi k e to the minus j k pi over 2, or pi k over 2. It's the same. Okay, so this is then, these are the Fourier series coefficients for all k except 0. But this may be a little further simplified, because I can see a few things here. It is 2 sine pi k over 2 e to the minus j pi k over 2 divided by j pi k all over squared, or pi square k squared. You may think of it like that, for k different than 0. This is now a little bit more handsome and compact. And that's it. You can give this as an answer. But of course, without the DC coefficient, it would be missing some part of the complete result. So let me also give you what C0 is. C0 is within one period, okay, the integral of the signal within a period, like from 0 to capital T. One period is 4, and the integral from 0 to 4 is 4 over 2, because 4 is the width of the triangle, and the height is 1. 4 times 1 over 2 is the area of the triangle. And over 4 will give you 1 over 2. Okay, for k is equal to 0, in other words, this is the answer that you have to give. So you should better give the answer in an examination and put it in a box like this with ck and c0, preferably separately, because joining them would be a little bit difficult. Okay, so this was another example. Now the next example is also related to the rectangular box shapes, so it is inheriting from that. And that in that example, now I have, I will start with one example first, and then the continuation of this example will be the example that I want to show you. But this example by itself is also quite important. You can even think of it as a property or a typical Fourier series calculation for a typical signal. There are some canonical or very typical signals. A rectangular box train is something like that. And this signal is also quite critical in that aspect. It's called an impulse train. And I'm gonna denote again this one by x of t, just the name. And it is impulses, periodic train of impulses like this, extending from minus infinity to plus infinity, like this. And it's clearly has a period. Let's say that the period is capital T. So it goes on like this on the time axis. What are the Fourier series coefficients of this impulse train? It's always a good idea to know the Fourier series coefficients of some very known signals. This is one of them. So please try to remember, and it's not very difficult to remember. And in a question format, it could also be written as x of t is equal to summation from minus infinity to infinity delta t minus k times capital T. This is the analytical way of putting the Fourier series coefficients. Now the Fourier series coefficients must be evaluated, and they will be evaluated using the integral, because this is a fundamental signal. So let's not hesitate applying the Fourier series coefficient formula. What was it? It was 1 over capital T integral within a period, let's say from minus t over 2 to t over 2. So I am taking the integral from here to here, okay, within one period where only a single impulse remains. And inside it, the signal is therefore that signal, that single impulse, which is the impulse delta t. And the formula tells me that it is multiplied by e to the minus j k omega 0, which is 2 pi over capital T t dt. So this is the integral, the formula. The formula may look a bit awkward or difficult looking, but it's not really difficult. There's nothing difficult about it. It's the integral of an impulse. What is the integral of an impulse? What's the area under an impulse? It is 1. It's the unit impulse times the scale at the position of the impulse. Where is this impulse? At which t value do we have the impulse? The impulse is, as you see, at t is equal to 0, okay? At t is equal to 0, there is an impulse. That is the position of the impulse. So at t is equal to 0, what is the exponent? E to the minus j k 2 pi over capital T times t. It is e to the 0, which is 1. So this is 1. The e to the blah blah thing is equal to 1. So at t is equal to 0, it is 1 times delta t's integral, and 1 times delta t's integral is 1. So the integral is 1 over capital T times 1, which is 1 over capital T, the AK, not the integral, but the Fourier series coefficient AK is therefore 1 over capital T. And that's an astonishing result, because it's valid for all, no, I should put it like this, for all K, including K is equal to 0, 1, 2, 3, minus 5, minus 7, 1 million, 1 trillion, they are all 1 over capital T. So this signal is quite a high frequency signal. It's quite a sharp signal. It never decays as the frequency increases. Normally, we know that the Fourier series coefficient magnitudes tend to decay. But for this one, it never decays. It stays constant. All the Fourier series coefficients have the same magnitude up until infinity. Because this signal is so high frequency that's what's happening. If the signal is impulse, it contains all the frequencies, every frequency, like the white noise kind of thing. But this is not random, of course. This is a deterministic very high frequency signal. It shows a very abrupt change. So the frequency content of this signal is practically infinity. So the Fourier series coefficients are all 1 over capital T, which makes a different definition of x of t using the Fourier series coefficients. You remember that? For all k from minus infinity to infinity, what was it? It was ak times the harmonic. So ak is 1 over capital T, and the harmonic is e to the j k 2 pi over capital T or omega 0, similarly, t, which can be written as this 1 over t can be taken out of it, and the same, k from minus infinity to infinity, e to the j k 2 pi over capital T, t. Now notice that these are sinusoids. Complex sinusoids, of course. But they are nevertheless consisting of a cosine term and a sine term. The sinusoids are like this. Now I want to show you an interesting thing, which I personally find very interesting, and I hope you guys will also be surprised about seeing this. This is an infinite summation of sinusoids. Which gives you x of t, whereas the top one here is telling me that the signal is an infinite summation of impulses. So the infinite summation of impulses is equal to infinite summation of sinusoids. That was a mathematical challenge. In other words, this was an Olympic question, a math Olympics question, but not in the grade of high school or anything like that. Advanced mathematical Olympiads I'm talking about. So the question was, show that that capital T can be taken as 1 if you wish. In fact, in the question probably it was 1, is equal to capital T times summation delta T minus K times capital T. Because without the knowledge of Fourier theory, Fourier series, Fourier transforms, etc., the things that you know now, without that knowledge, if somebody would ask you to prove this equality that you see on the screen, you would just stare at it, gaze at it, and say, well, wow, how can it be? The left-hand side is a summation of sinusoids, the right-hand side is the summation of shifted impulses. How can they be the same? But now we know they are the same. So it was something that I always find interesting. Now, this impulse train is there, but we can also make some extensions of this example to formulate the Fourier series coefficients of a rectangular box now, because a rectangular box can be obtained as integral of impulse train, two impulse trains, or you can see that in the rectangular box there is an upgoing discontinuity of the box, and then downgoing discontinuity. One of them will make an upward or magnitude 1 impulse, and the other one will make a negative impulse. What I'm trying to say is actually this signal. We have 1 as the impulse here at minus t1 and negative 1 at t1. These two impulses. And with a period of, let's say this is capital T over 2, and this is capital T. Around capital T, we again have these two impulses of 1 and minus 1. at capital T plus T1 and at capital T minus T1. So this bunch is being repeated here, and it also appears here and there, etc. It is periodic with capital T on the time axis. Let's give a name to this. Let's call it Q of T. Okay, and that Q of T is equal to, in terms of X of T that we have here, the impulse train, it's equal to X of T plus capital T1 minus X of T minus capital T1. So one of them is shifted to the left by capital T1, and the other one is shifted to the right by capital T1 and multiplied by -1. That's why we have a minus sign in between two X terms. And now we can use the linearity and time shifting properties to find the Fourier series coefficients of this and this separately, and then we will combine the Fourier series coefficients of both of them. The Fourier series coefficients from here will be equal to e to the jk omega 0, which is 2 pi over capital T, times T1, capital T1, AK, but I know that AK is 1 over capital T, so remember that. And for the other one, it is e to the minus jk omega 0 capital T1 times AK, and I put a minus sign in between, and these are the Fourier series coefficients of BK, which I can call BK is equal to this, okay, using the linearity property. So these are the Fourier series coefficient pairs. The right-hand side of the equation can now be normalized to 1 over capital T, because AK is 1 over capital T. And then I want to do it like this, in parentheses, e to the jk omega 0 T1 minus e to the minus jk omega 0 T1. And I want it to look like a sine, using the Euler formula, or Euler expansion of sine, where we should have it over 2j from the formula. So I put in over 2j, and in order to compensate for that, I'm going to multiply everything with 2j. So 2j's will cancel. But I don't want to cancel them because I need it in this format, where this thing is essentially sine k omega 0 T1. Therefore, this is equal to 2j over capital T sine k omega 0 T1. This is BK. These are the Fourier series coefficients of these plus positive, negative, positive, negative, positive, negative impulse train. Excuse me. Let's keep those in our minds, and let's continue with another example where we now integrate this Q of T to obtain the rectangular box train, which is like this. This is capital T, this is T1, this is minus T1, and this is 1. We can give a name to this one. Let's again call it G of T on the time axis. Do you see that when you take the time derivative of G of T, you get Q of T, the top, the signal that is drawn at the top, okay? So this is the integral of it, of that one. G of t is the integral of Q of t. Oh, sorry, Q of t is the integral, Q of t is the, yeah, the same thing. Q of t is the derivative of G of t. So Q of t is the time derivative of G of t, which tells me that G of t, whose Fourier series coefficients can be called CKs, and Q of t has Fourier series coefficients called BKs, which is 2j over capital T sine k omega 0 t1. We found it here. It was here. So from there, CK must be equal to 1 over jk omega 0, right, times 2j over capital T sine k omega 0 t1. It must be like this. Now let's try to simplify it a little bit. The j's will go away and we will have 2 over k times omega 0 is 2 pi over capital T, and then we have capital T again times sine k omega 0 t1, and that is equal to, these t's will also be cancelled. The j's were cancelled already here, and the 2's will cancel, and I will have sine k omega 0 t1 divided by k times pi. Surprise, surprise. Of course, there is no surprise, because this was already the Fourier series coefficient formula for this rectangular box train using the formula that we found. Taking the integral, we got this. You can check out our previous notes if you wish. You will see that these are the Fourier series coefficients. These were the Fourier series coefficients. And from this example, we again found it to be equal to the same, exactly the same expression. I would say for k different than 0, because if k is equal to 0, it's a 0 over 0 ambiguity. So it's always safe to find the C0 value separately. But for all others, it's this. And for k is equal to 0, it's again this, by the way, because sine 0 over 0 ambiguity can be handled by the Hospital's rule, L'Hopital rule, and you take the derivative of the numerator and the denominator separately, and it will give you, I think, capital 2 capital T1 over capital T or something like that. You will still find the same formula. The result is not a surprise, but it's a relief. We are now confident that all these properties are compatible with one another. They should be compatible. They are not God-given properties. There are proofs of those things. Mathematically, everything is consistent. So if you ever forget the Fourier series coefficient formula of a rectangular box, you may just find it using the formula of what is AK, what are the Fourier series coefficients. It was an integral formula, as we remember. But even that formula you may not remember, but instead you may remember that the impulse train Fourier series coefficients are all 1 over capital T, and you know the derivative property. From there, it is still possible to come up with the Fourier series coefficients values of the rectangular box train. So everything is consistent with one another. This was one very important example that I would really like to show you. And before proceeding with other examples or other exercises, I want to give a break at this point, and we will continue at 3 o'clock. We will continue with 1 more hour starting at 3 o'clock. So I'm stopping at this point. You may think of questions if you may construct from these things that we have seen. At the beginning of the 3 o'clock lesson, you can ask them. Right now, I'm just stopping and leaving. We will meet at 3 o'clock at the same place. So take care.